that means T1 has increased with the measurement. And that's because this case here, where we're on this peaked on the center of the density states, at detuning 0, we're able to sample, on average, less photons of the thermal bath. And then we see here where the T1 changes, T1 decreases, and that's the anti-Zeno effect. Okay. But let's look a little deeper into the measurement interaction. I want to get back to this, the question of Schrodinger's cat. Is it the, in fact, let me just skip this slide. The point is, my question I want to ask is, we're measuring the qubit. Is it the fact that we're collapsing it to its ground or excited state that's causing the T1 to change? Or is it the fact that we're just disturbing it? Which one is the effect? Is it sort of this idea that you collapse it and still restart the decay process or not? And so to test that idea, I want to design a measurement that collects no information, okay, what we call a quasi-measurement. So in order to understand this, here's one way you could measure the qubit. This would be an actual measurement. What we do is we take another state of the qubit. When it's in this excited state, we'll excite it up to the F state and let it decay down by spontaneous emission. So we've put a detector there. We'll detect that emitted photon, and we'll know, it must have been an excited state. If it's in the ground state, this transitions off resonance, and there'll be no photon emitted. So that's a projective measurement onto the excited state or the ground state, the detection or not detection of a photon. Okay, so instead, I want to do something that is a little stranger. What I'm going to do is I'm just going to do a pi pulse up to the excited state, second excited state, and then I'll do a pi pulse back down. So I'm going to take the qubit out of its manifold and back down. And what this actually does is this relative phase of these two pulses imparts a Berry phase on the qubit. I can't remember who was it who talked about it in their talk at the last thing. He talked all about this NV experiment where they did this Berry phase. It was maybe it's Guido who's talking about this experiment. Anyway, at the conference last week, so for the 3 or 4 of you who were there. So it's exactly the same thing. So here's a Ramsey measurement to measure this Berry phase. We're just going to apply a pi/2 pulse, do this thing, and then we'll apply another pi/2 pulse. And as I change the phase between these two pulses, we see that we see a Ramsey go through a Ramsey fringe. So this pulse just adds a phase to the qubit. So the idea of a quasi-measurement is to randomize this phase. Therefore, we'll completely dephase the qubit. Averaging over this, we'll get a half. Okay, but there's no information accumulated about whether the qubit's in the ground state. So this is disturbance without information. Okay, so let's see if these Zeno effects occur when you do disturbance without any information. Okay, so pi pulse, measure. These are quasi-measurements. Do readout for a T1 measurement. And we see, look, just as before, we see this Zeno effect and the anti-Zeno effect, just as we did with these projective Z measurements. So the conclusion is these quasi-measurements induce Zeno effects the same way as the measurements that collapse the wave function. So it all comes down to the qubit spectrum, that is whether or not we're seeing more density of states or less density of states, or more thermal photons or less thermal photons. And you could check this by just checking how the qubit line changes as we add measurements. So here's the sort of bare line, slightly power broadened in black. And then as we make measurements at higher and higher frequency, so first at 1 every 500 nanoseconds, 1 every microsecond, 1 every 2 microseconds, or vice versa, every 2 microseconds, every microsecond, every 500 nanoseconds, you can see the line broadens and spreads out as we dephase it and sort of modulate it.
Is this spectroscopy?
So spectroscopy. So we're just going to do a sort of weak continuous spectroscopy while applying these measurements.
So which type of measurement is this?
This is the dispersive Z measurement. Okay? But when I do these quasi-measurements, that's these MMM, we see the same effect on the qubit line. Both of them broaden the line, therefore both of them cause these sort of Zeno and anti-Zeno effects. So to summarize what we've learned, come back to Schrodinger's cat. The idea behind the Zeno effect is if you measure it quickly enough, you keep collapsing the cat back to its alive state, and thereby prolonging its life. But as I showed, under certain circumstances with the bath and the qubit, if you measure fast enough, you can end up killing the cat. Zeno effect, anti-Zeno effect. But the take-home message here is it's not necessary to look inside the box at all. In fact, all you have to do is shake the box. And that's enough to cause these Zeno effects to occur. So, say shake the box. All right. So the takeaway message is that both of these effects, we observe both these effects, these quasi-measurements, show that collapse is not important. And the idea is that we can alter this decay process with measurement. And maybe that's interesting. What if this bath wasn't just some thermal photons, but it was actually structure in the electromagnetic vacuum? Then you can imagine these measurements causing the qubit to actually enter into interesting superposition states and so forth, induced by measurement. I know that there's also this phenomenon of xenodynamics. I know the folks at Berkeley have a very nice result coming out where they're able to create entangled states of two qubits through similar effects. So there's certainly extensions to these ideas. That will be fun. Okay, that's the end of my talk. Just 2 minutes over. I'll just acknowledge Matthew Nagaloo, this guy here, who did the work on the frequency metrology, and then Patrick Harrington, who's the other guy climbing on the tree, who really spearheaded the Zeno effect experiment. So thank you for your attention.
Okay. Any more questions? I have a bunch of them.
Okay.
So, saying that by applying 2 pi by 2%, you are not really applied information.
Yeah.
I think you have still some information that if the state is not there, some other state will do something with the state.
So the question is, does a pi pulse on a qubit measure whether it's in that state or not? And the answer is, in the limit where there's a classical drive containing an infinite number of photons, there's no information accumulated. I think for a quantum drive where you can actually accumulate information. You can learn whether the qubit's there by applying a pi pulse on it. But in general, no, in the limit of a classical drive, there's no information accumulated about the state. So vanishingly small information. But it's an interesting question about whether these pulses, in principle, acquire information. But certainly, if there is any, it's incredibly small.
So maybe I had a little question. In the second type of experiment, one with the very first cell, when you set M, when you're doing this many M's, the M is just the 2 pi pulses?
Yeah, so we just do
So the Ramsey experiment following the M was just a verification that you're getting this verification.
So we do a pi pulse, and then we do so we do this initial pi pulse to prepare the qubit, and then we just do pi pulse, pi pulse, pi pulse, pi pulse, pi pulse, pi pulse. They look like M's.
You're doing 2 pi pulses, 2 pi.
Yeah. So but one of them's with one phase, theta 1, and the other one's with another phase, theta 2. In the second phase, we choose from a pseudo-random number generator. So we're always applying a random phase. So because these have random phase, after this, it completely decohered any sort of superposition. So it's just sort of decoheres any possible superposition between the ground and excited state, and that's all it does.
Okay, so then the only pulses are the 2 pi pulses. There's nothing else going on.
Yeah, it's just 2 pi pulses back to back.
So with measuring the anti-Zeno effect, it seems like to me that by moving around your omega zero, by moving it left and right, you can very sensitively probe exactly what the shape of the distribution function is. Is that right?
So, well,
it's uninteresting.
absolutely. So, well, without the Zeno effects and the anti-Zeno effects, just with looking at T1, you can probe the shape of the bath. And this is something that people thought about very early with these qubits, is that it's a very good spectrum analyzer for this sort of environment it has. Because you see that same shape, you saw the T1 dip, that's a perfect reflection of the number of photons in the bath. Now, when we do these Zeno effects and anti-Zeno effects, that's a convolution of the qubit line shape under this perturbation and the bath. So it's a little more, you have to deconvolve the two. So there, it's a little hard to learn directly about the bath, but certainly the qubit coherence is a way to probe the structure of the bath.
So I have another, so maybe you mentioned this experiment coming from Berkeley, and maybe that's the same thing. So it's like this thing about both of your techniques for measurement are doing something to the qubit, whether it's a cavity drive or whether this pi pulse drive. But if you do the textbook picture of weak measurement or variable strength measurement, where take one qubit and tangle with another qubit, do a projected measurement on this guy to get an effective measurement on the first one. Is that what the Berkeley experiment is? And you see the same effect?
So the Berkeley experiment is doing, if you ask Emmanuel Florin, he says it's pure Zeno effect. It's just dephasing. That's like what they're doing. So they're dephasing a certain level. They have this, I don't know, you can think about the 2-qubit subspace. You have these levels here where they're both up and they're both down, and then we have up, down, down, up. They're driving something, and they're using dephasing to sort of eliminate one of these from the manifold. I don't exactly know what they're doing because I haven't read the paper or seen the talk.
But what, I think in an earlier discussion, maybe when I visited you, this measurement without information, we talked about using turning the param to measure the wrong quadrature.
So that was the part I kind of skipped, is that in principle, this dispersive measurement, there's two types of back action. One is like you're learning about whether or not it's in the ground or excited state, and one is you're dephasing the qubit, and you can control which one you have with the type of phase or amplification. So, very technical point. That's very interesting. So that was kind of going to be my motivation for trying this quasi measurement. What if you could because in principle both of those are happening given our finite quantum efficiency. What if you could choose just one of them and not the other? And that's what we've done in the limit of an infinitely strong measurement with these randomized Bary phases.
Because I think it's sort of a subtle distinction between, is this a completely classical effect? You're sending a field to your qubit, you're changing how it responds to the environment, and in the case where you're, say, detecting the wrong quadrature, the cavity field is always there. You're saying that, okay, this is a purely back action effect. It doesn't seem to matter whether you collect information or not. Versus something more subtle, and maybe your second measurement does prove that. We know that this is actually on
I have the
measurement.
same feeling that
Or is it
might just be system shift.
Or is this back action?
I'm not sure.
I mean, I think the point is there's no, with these quasi measurements, I think there's not back action in the quantum measurement back action sense. It's a much more contrived sense of measurement. It's similar to a measurement in that at the end of the day, when you make we take our qubit, we measure just the quadrature that carries photon number information. And therefore we have information about the cumulative phase of the qubit, but we haven't projected it toward its eigenstates. At the end of the day, we have a correlation between the phase of the qubit and some number we have in our digitizer. Okay? In this case here, we choose a number with our random number generator, and we imprint that phase on the qubit. There's still a relationship between a number we have stored on the computer and the qubit. So the end of the day effect is the same. But I don't know, the interaction's a little more contrived. Does that tell us something deep about what quantum measurement means? And maybe it does. There's no entanglement involved. There's no two quantum systems that are entangled, and there's no steering or anything like that involved. But the end of the day effect is the same. So.
Okay. Any questions? If not, we can continue. There's going to be tea at the West Camping, so we can continue the discussion. Let's thank Kevin again for.
Thank you.